The Sun is so large that 1,000,000 Earths would fit inside it, with room left to spare, and every heartbeat you have ever had was paid for by its light. It sits at the center of everything we are, close enough to warm a cheek, far enough that its light takes 8 minutes to reach us, and for most of human history, something in its atmosphere runs hotter than physics says it should. Something in its magnetic heartbeat refuses to be predicted. Something in its long-term rhythm looks like it is running quieter than it ought to be. And the people paid to model our star for a living are the ones saying so. Before this is over, we are going to walk through the 1,000,000-degree corona that should not exist, the weakening cycle nobody can fully explain. If wonder like this is what keeps you up at night, take a moment to like and subscribe. We begin. Start with the number, because the Sun holds roughly 99.8% of all the mass in our solar system. Every planet, every moon, every asteroid and comet and grain of dust orbiting out past Neptune amounts to a rounding error. Its diameter runs to about 1.4 million kilometers, which means you could line up more than 100 Earths side to side across its face. Its core burns at somewhere near 15 million degrees Celsius, a pressure-cooked furnace fusing hydrogen into helium at a rate of roughly 600 million tons every second. Every second, the Sun releases more energy than humanity has produced in its entire recorded history. It has been doing this for 4.6 billion years. And yet the strangeness we are about to walk through is not happening in some distant, unreachable part of that furnace. It is happening in the parts we can see. It is happening in the layer closest to us, the one you can watch flare and twist through a solar telescope on any clear day. That is what makes it unsettling. It is a mystery sitting in plain sight on the most observed object in the sky. The first serious modern measurements of the Sun's outer atmosphere came together in fits and starts across the early 20th century. Astronomers pointed spectrographs at the pale halo visible around the blacked-out disk during totality, the corona, expecting to read off a temperature somewhere close to the surface. Instead, in 1941, the Swedish astronomer Bengt Edlund, building on work by Walter Grotrian, identified strange spectral lines in coronal light as highly ionized iron. That kind of ionization does not happen at 5,000 degrees. It requires temperatures in the millions. The scientific community, it was catastrophically, almost nonsensically hot, and hotter than the surface directly beneath it. That finding, confirmed and refined through the ground-based coronagraphs of the following decades and later by spacecraft instruments built specifically to stare at the corona in ultraviolet and X-ray light, became one of the founding puzzles of modern solar physics. it has never fully gone away. It is worth pausing on how strange this would have sounded to any earlier generation of astronomers. For as long as humans had studied the sun, the working assumption, borrowed from ordinary experience with fire and heated metal, was that anything glowing around a hot object had to be cooler than the object itself, fading gradually. Edlin's identification of highly ionized iron in the corona's spectrum inverted that assumption for the single most observed object. It meant the faint, pale halo, visible only during the fleeting minutes of a total eclipse, was, invisibly, far more violent than the blinding disk it surrounded. That inversion is why the corona heating problem is often introduced to new students of astrophysics as one of the cleanest examples in the entire field of a measurement simply refusing to fit the intuitive picture, a puzzle hiding not at the edge of the universe, but in our own sky, on a clear afternoon. If you know how to block out the light beneath it, here is the shape of it, stated as plainly as it can be stated. The visible surface of the sun, the photosphere, sits at roughly 5,500 degrees Celsius. Move outward, away from the furnace, and by every ordinary rule of physics, the temperature should drop, the way air cools as you climb away from a campfire. Instead, just above that surface, the temperature spikes to 1 million degrees Celsius. In some active regions, it climbs past 3 million. It is moving uphill, away from the source, and getting stronger the farther it moves from where it was made. For more than 80 years, this has been one of the most stubborn open problems in astrophysics, hiding not in some remote corner of the universe, but a few thousand kilometers above the surface of the nearest star, in a place scientists have photographed, mapped, and modeled more times than almost any other feature. The mechanisms proposed to explain it are not vague guesses. They are two serious, competing physical models, both partially confirmed. Neither one declared the full winner. In this picture, the roiling motion of the sun's surface, the constant churn of convection cells, the size of countries, sends magnetic waves called Alphen waves up through the atmosphere. These waves ripple along magnetic field lines the way a plucked guitar string sends vibration down its length, and when they reach the thin plasma of the corona, they dump their energy there, heating it. Spacecraft have detected these waves. They are real. What remains unconfirmed is whether they carry enough energy. The second model is called nanoflare heating, and it comes from the physicist Eugene Parker, the same researcher for whom the Parker Solar Probe is named. Parker proposed that the corona's magnetic field lines, anchored in the churning surface below, get twisted and stressed as that surface moves the way you might twist a rubber band by turning one end while holding the other still. Eventually, the tension exceeds what the field can hold, and it snaps, releasing energy in a burst too small and too fast to see as an individual event. Both wave heating and nanoflare heating have observational support. Neither one, on its own, closes the books on the problem. Most working solar physicists today suspect both mechanisms are operating together in some ratio nobody has pinned down, which is itself an admission. After 80 years, we still cannot fully say why the outer layer of the nearest star is hundreds of times hotter than the surface it surrounds. It gets stranger when you consider the million-degree corona is what allows the sun to blow the solar wind, the constant outward stream of charged particles that fills the entire solar system. Get the corona's temperature wrong in a model, even slightly, and the predicted solar wind speed comes out wrong, which means space weather forecasts come out wrong. Unsettled physics, dressed up as settled science. Every spacecraft that has ever measured the solar wind, from the first probes of the 1960s through the fleet of monitors watching today, we fly instruments through the answer to a question we have not finished asking. Modern X-ray and ultraviolet observatories, from the Japanese-led Yoko mission of the 1990s to the Solar Dynamics Observatory that has watched the sun. These instruments can now resolve coronal loops, the glowing magnetic arcs threading up out of active regions, in enough detail. What they show is a corona heated unevenly in patches and threads, rather than as a smooth, uniform shell consistent with either wave heating or nanoflare heating, concentrating energy in narrow magnetic structures. That patchiness is itself a clue, but it has not yet been enough to let researchers write down a single equation. 80 years after Edlund's spectral lines first forced the issue, the corona remains one of the few places in modern astrophysics where you can point a well-funded Here is the part that matters next. The sun does not simply burn at a constant, reliable pace. It runs on a magnetic cycle, roughly 11 years long, swinging between a quiet minimum, when sunspots are scarce and the surface looks calm. This rhythm was first documented systematically in the 1840s by the German astronomer Heinrich Schwabe, who spent 17 years counting sunspots. For more than a century, that 11-year rhythm has been treated as one of the most dependable heartbeats in the solar system. Solar Cycle 25 is the most recent example, and it embarrassed its own forecast. In the years leading up to its onset, the official panel convened by NASA and the National Oceanic and Atmospheric Administration, drawing on decades of prediction models, instead, sunspot activity climbed faster and higher than the panel's own consensus curve, arriving stronger and earlier than predicted, catching forecasters visibly off guard in real time, with revised outlooks issued mid-cycle to catch up with what the sun was actually doing. This was not a fringe miss. It was the official, multi-agency, multi-model prediction built from our best understanding. The deeper unease is not that one forecast missed. It is that solar cycle prediction as a discipline has a poor track record stretching back decades. Missing amplitude, missing timing, sometimes missing the shape of the curve entirely, despite pouring in helioseismic data, surface magnetic field measurements, and increasingly sophisticated dynamo models. We can predict eclipses to the second centuries in advance because gravity. We cannot predict with confidence how strong our own star's next magnetic cycle will be, because the dynamo generating that cycle, the churning interplay of plasma flow rotation and magnetic field deep inside the sun remains only confirmed. The 11-year cycle exists, has existed for as long as records go back, and is driven, still not understood precisely what combination of internal flows sets the amplitude and timing of any given cycle far enough in advance to trust the forecast. We are, in a very real sense, guessing about the near future behavior of the star that determines whether our satellites survive the next decade. A star's magnetic cycle is not cosmetic. It governs how many flares erupt, how many coronal mass ejections get flung toward Earth, how radiation levels shift for astronauts and high-altitude flight crews. A forecast that misses by this much is not a rounding error in an abstract science. It is the input variable for how we plan space weather defense for the next 10 years, built on a model of our own star's engine. The panel responsible for the Cycle 25 forecast did not make its prediction casually. It combined two competing methodological camps, one relying on precursor methods that use the strength of the declining previous cycle to estimate the next one. The kind of multi-method agreement that normally inspires real confidence in a forecast. That consensus still undershot what actually happened, and revised, more aggressive outlooks had to be issued after the cycle was already underway. A discipline capable of that kind of mid-flight correction is a discipline that, by its own admission, is still reacting to the star rather than anticipating it. It gets stranger still. Solar Cycle 24, which ran from roughly 2008 to 2019, was markedly weaker than the 20th century average. Cycle 25, despite outperforming its own gloomy forecast, still sits below the long-term historical mean, measured across the last several centuries of sunspot records. Solar physicists have been watching this multi-cycle softening and asking cautiously whether the sun is drifting toward what is called a grand minimum, an extended stretch of suppressed magnetic activity. The reason that question carries weight instead of being dismissed outright, is the historical precedent confirmed through both sunspot records and indirect proxies, documented at the time by astronomers, including the pioneering observer who lent the period its name. Only about 50 sunspots were recorded across those 70 years. The Maunder minimum coincided closely with the coldest decades of what climatologists call the Little Ice Age, a period of markedly harsher winters across parts of Europe. Correlation is not the same as proof of causation, and solar physicists are careful to say the Little Ice Age had multiple contributing drivers, including volcanic activity. It sits in the literature as a real, still debated relationship. Here is the part that matters. Nobody is claiming we are entering another Maunder minimum. The data does not support that strong a claim, and Cycle 25's stronger than forecast performance arguably argues against it. What working solar physicists are documenting carefully and without sensationalism is a multi-decade softening trend, layered on top of a cycle we already cannot forecast reliably, raising a question serious researchers are willing to ask in peer-reviewed venues: is the dynamo generating our star's magnetic field entering some kind of longer, and if it is, what does that mean for a technological civilization that did not exist the last time this happened? 3.5 centuries ago, a quiet sun mostly meant colder winters. Today, a materially different solar activity regime would ripple through satellite drag models, high-frequency radio communication, and the baseline assumptions built into space weather forecasting. We watched the metronome skip once with Cycle 25. We do not yet know if it is preparing to skip in a much larger. Researchers reconstruct these longer solar rhythms using proxies that reach back far beyond the era of telescopic sunspot counting, most notably both produced at rates that shift with the strength of the sun's magnetic shielding against incoming cosmic rays. Those proxy records show that grand minima, similar quiet intervals, appear to have recurred multiple times over the past several thousand years, spaced irregularly. That irregularity is precisely what makes the current softening trend hard to dismiss and hard to confirm at the same time. It does not say when or whether it is about to do it again. Here is where the dread deepens, because this next chapter is the story of an anomaly that took nearly 40 years to resolve, and for most of those decades, the honest answer was that the data beginning in the late 1960s, the American chemist Raymond Davis Jr., working with a giant tank of cleaning fluid buried nearly a mile underground in the Homestake gold mine in South Dakota, set out to detect neutrinos, the nearly massless, ghostly particles produced in vast quantities by the fusion reactions. Theoretical models developed alongside Davis's experiment by the astrophysicist John Barkhoule predicted a specific incalculable flux of these particles reaching Earth. When Davis counted what his detector actually caught, he found only about 1/3 of the predicted number, not a small discrepancy, a persistent, replicated shortfall, confirmed again and again over decades of running the experiment and reproduced by later detectors using different technologies. For years, this was treated inside the physics community as a genuine crisis, dryly named the solar neutrino problem, and it forced an uncomfortable question: was our model of how the sun burns wrong? Some solar physicists worried the core temperature or fusion rate calculations underpinning all of stellar astrophysics might need revision, which would have been an admission. Others suspected the flaw lay in particle physics rather than solar physics, a controversial position at the time because it required something genuinely strange to be true. The resolution, when it finally arrived, was more remarkable than either camp expected. Data from Canada's Sudbury Neutrino Observatory in the early 2000s, building on earlier hints from Japan's Super Kamiokande detector, confirmed they oscillate, shifting identity between 3 different types as they travel, and Davis's original detector had only been sensitive to one of those 3 types. 2/3 of them had simply changed into a form the detector could not see. The fix rewrote a piece of particle physics, confirming that neutrinos have mass, a finding significant enough to earn the 2015 Nobel Prize in Physics for the leaders of the Sudbury. The sun, in the end, was innocent. But for nearly 40 years, one of the most basic predictions we could make about our own star, how many ghost particles should be pouring out of its core every second, did not match what our instruments recorded. That is worth sitting with. For 4 decades, the numbers from the nearest star in the universe did not add up, and the smartest people alive. What makes the episode worth returning to now is not just that it was solved, but how narrowly it could have gone the other way. Barkol himself spent much of his career defending the standard solar model against the possibility that the core temperature or the nuclear reaction rates powering the sun He held that position through decades of being the one experiment's numbers away from being wrong about the object he had spent his life. Solar neutrinos are still monitored today at facilities including Sudbury's successor experiments and Italy's Borexino detector, and they now match prediction. But the problem is a permanent reminder that even the most basic, most fundamental output of the sun, the neutrinos, streaming from its core every second. Here is what makes the modern stakes different from anything in that history. In late August and early September of 1859, the English astronomer Richard Carrington was sketching sunspots through a projected telescope image when he witnessed an intensely bright flash. Less than 18 hours later, a coronal mass ejection, tied to that flare, slammed into Earth's magnetosphere, a transit time so fast. The effects were not subtle. Auroras, normally confined to polar latitudes, were reported as far south as the Caribbean and Hawaii, bright enough in some locations that observers could read a newspaper by their light at midnight. The telegraph network, the entire planet's long-distance communication backbone at the time, was thrown into chaos. Operators reported sparks leaping from equipment, some receiving shocks, some describing paper igniting under the telegraph keys from induced. In several documented cases, operators disconnected their batteries entirely and continued sending messages powered purely by the current the storm itself was inducing in the lines. This is confirmed, extensively documented history, corroborated by observatory records, newspaper accounts, and telegraph company logs across multiple continents. In 1859, the technological footprint vulnerable to that kind of geomagnetic storm was essentially one network: telegraph wires. Transformers on continent-spanning power grids, satellites in every orbital band, GPS timing, signals underlying financial transactions, and cellular networks. High-frequency radio used by transoceanic aviation, undersea data cables with vulnerable long-haul repeaters. A Carrington scale event striking today's infrastructure would not produce a curiosity about sparking telegraph keys. Modeling conducted by government agencies and insurance industry risk analysts in the years since has estimated that a direct hit from a storm of that magnitude could damage or destroy large numbers of high-voltage transformers, components that in many cases take months to manufacture and are not kept. Potentially leaving parts of continents without grid power for an extended period while replacements are built and shipped. Confirmed, the 1859 event happened, was extreme, and its scale has been reconstructed from multiple independent data sources. Not resolved how well our modern grid would actually withstand a repeat, because we have never had to find out. Modern researchers have gone back to the surviving magnetometer records from observatories around the world, including data from Colaba Observatory in Bombay. And the reconstructions consistently show a geomagnetic disturbance more intense and more rapid in onset than nearly anything measured in the century and a half since, including the severe 1989 storm that knocked out the entire Hydro-Quebec power grid in Canada within about 90 seconds, leaving 6 million people without electricity in the middle of a March night. That 1989 event, serious as it was, it is one of the closest modern comparisons we have to work with, and it still fell short. It gets stranger, because we very nearly did find out. On July 23, 2012, an extraordinarily powerful set of coronal mass ejections erupted from the Sun, launched from an active region that had already produced a series of X-class flares. Instruments aboard NASA's Asterio-A spacecraft, positioned in an orbit that happened to be looking at exactly the right patch of space at exactly the right time, in some analyses potentially exceeding it. The only reason this event did not become a modern Carrington disaster is a matter of timing that had nothing to do with any defense. The active region responsible for the eruption crossed the same point in the Sun's rotation that faces Earth roughly 9 days after the eruption actually occurred. Had the same series of flares and ejections happened just over a week earlier or later in that region's rotational cycle, NASA solar physicists who studied the event afterward, including Daniel Baker of the University of Colorado, went on record describing the near miss in stark terms, noting that had it hit Earth, the resulting damage to satellites, communications, with recovery estimated to take years rather than months in the hardest hit regions. Here is what makes this genuinely unsettling, stated as plainly as the researchers themselves stated it. This was not a near miss detected by some elaborate planetary defense system. It was a matter of 9 days of solar rotation, tracked only because a spacecraft happened to be parked in the right place to see it, studied only in retrospect once the data came back. We do not have continuous, redundant, all-angle coverage of the Sun's Earth-facing side, ready to catch every event like this. We got lucky in 2012. We know we got lucky because the physics of the rotation and the timing are fully reconstructed and confirmed. Confirmed the 2012 event happened, was Carrington class or larger, and missed Earth by a matter of days. Still unresolved how much genuine warning time we would actually have the next time the timing runs the other way. The current early warning system for events like this relies heavily on spacecraft stationed at a gravitationally stable point called L1, roughly, both of which sample the actual solar wind and magnetic field only shortly before it reaches Earth. That arrangement typically buys a warning window of perhaps 15 to 60 minutes between detection at L1 and impact, enough time to take some protective measures on satellites and power grids, but nowhere near enough time to manufacture a replacement transformer, reroute a continent's power distribution, or evacuate any hardware. The 2012 event was reconstructed only after the fact from data gathered by a spacecraft that happened to be watching from the side. Our actual operational forward warning system, watching for a storm aimed directly at us, still measures its lead time in tens of minutes, not days. Here is the part that matters next, and it comes from the closest anyone has ever gotten to answering these questions directly. NASA's Parker Solar Probe, launched in 2018 with a mission unlike anything flown before, fly a spacecraft directly into the Sun's outer atmosphere. measure the conditions driving the corona heating problem and the solar wind from the inside, rather than reconstructing them from 100 million miles away. Over a series of increasingly close orbits, using gravity assists from Venus to tighten its path, Parker has now flown through the corona multiple times, at one point passing within about 6.1 million kilometers of the Sun's visible surface, closer than any human-made object in history. What it found did not simply confirm existing models. It surfaced entirely unpredicted phenomena. Chief among them, magnetic switchbacks, sudden, sharp, zigzag reversals in the direction of the Sun's magnetic field embedded within the outward-flowing solar wind, occurring in clusters. Nobody had predicted structures like this in such numbers before Parker's instruments recorded them directly. Researchers on the mission team, publishing results through NASA and in journals including Nature, described the switchbacks as potentially tied to the same magnetic reconnection processes theorized in the nanoflare heating model, but their sheer abundance and structure went beyond what any single existing theory had specified in advance. Confirmed, switchbacks are real, common, and directly measured. Still not understood precisely what generates them in this quantity and what role they play in accelerating the solar wind to the speeds observed further out. Parker also confirmed something theorized decades earlier but never directly measured: a dust-free zone encircling the Sun, a region where interplanetary dust, the fine debris that fills the rest of the solar system, has been almost completely vaporized or swept away by intense solar radiation. Exactly as predicted by models dating back to the 1920s, but only confirmed observationally when Parker's instruments flew through the region. And perhaps most significantly, Parker measured in real time the exact zone where the solar wind transitions from subsonic to supersonic flow. Before Parker crossed it in April of 2021, that boundary existed only in models. Now it has been measured directly, and it turned out to be more complex, wrinkled, and variable in position than the smooth surface earlier models had assumed. Here is the part that matters. Even a spacecraft built specifically to fly into the answer came back with new questions rather than a tidy confirmation of the old ones. It complicated it. Parker was built to survive conditions no earlier spacecraft had been engineered to withstand, protected by a heat shield made of reinforced carbon-carbon composite, roughly too capable of facing temperatures near the Sun that reach approximately 1,400 degrees Celsius on the Sun-facing side. The mission has now completed more close approaches than originally planned, with its final planned perihelion passes bringing it to within roughly 6.1 million kilometers of the photosphere. Every one of those passes has returned more switchback detections, more turbulence data, and more raw material for a still unfinished theory of how the corona is heated. a mission built to close the corona heating problem, has so far mostly proven how much more textured and complicated that problem is. It gets stranger when you leave the atmosphere behind and ask a more basic question: what is the sun actually made of? And do our two best methods of finding out agree with each other? For decades, solar composition was calculated primarily through spectroscopy, reading the specific wavelengths of light absorbed and emitted by different elements in the sun's outer layers. In parallel, an entirely different technique called helioseismology developed using the sun's surface oscillations, the whole star ringing very slightly. Essentially, by listening to the sun the way seismologists listen to the interior of the Earth through earthquake wave. For years, these two methods, one reading surface light, one reading interior vibrations, agreed closely enough to reinforce confidence in both. Then, in the early 2000s, a team of astronomers, led by Martin Asplund, published a revised set of solar abundance measurements using improved three-dimensional models of the solar atmosphere. The revision lowered the calculated abundance of key elements, especially carbon, nitrogen, oxygen, and neon, by a significant margin compared to earlier tables. When solar physicists plugged the new improved abundances into their standard solar models and compared the predicted interior structure against the actual helioseismic measurements of sound speed profiles deep inside the sun, the new composition numbers, believed to be more accurate, produced a model sun whose interior did not sound the way the real sun actually sounds. This discrepancy, known in the field as the solar abundance problem or the solar opacity problem, remains genuinely unresolved. Proposed fixes have included revised opacity calculations, the physics governing how efficiently radiation moves through solar material, and suggestions that the models of convection near the surface need further refinement, and neither route has fully closed the gap as of the most recent published analyses. Confirmed, two independently developed, historically reliable methods for determining what the sun is made of currently disagree with each other in a way that has resisted a decade and a half of proposed solutions. Still not understood which method or which underlying model assumption is actually wrong. We have built two different ways of asking the sun what it is made of, gotten two different answers, and have not yet worked out which one to trust or whether both need to change. The stakes of this disagreement reach well beyond the sun itself, because the standard solar model, calibrated against our own star's measured properties, is the baseline against which astronomers calibrate models of every other star in the galaxy. If the sun's true composition sits closer to the older, higher abundance values, our models of stellar evolution generally hold steady. If the newer, lower abundance values from the Asplund analysis turn out to be correct, and the discrepancy is instead hiding in some other unaccounted physical process, corrections. Directly or indirectly back to solar calibration. A disagreement that sounds like a narrow technical dispute over carbon and oxygen abundances in one star's outer layers is underneath it. Here is the part that matters at the edge of everything the sun touches. The sun does not simply sit in empty space. It blows a vast bubble around itself called the heliosphere, inflated by the constant outward pressure of the solar wind, extending far beyond the orbit of every planet before it finally meets resistance from the interstellar medium, the thin gas. For decades, the size and shape of that bubble were modeled mathematically, estimated from theory, because no instrument had ever measured its boundary directly. That, NASA's Voyager probes, launched in 1977 and still transmitting after more than 4 decades of flight, became the first human-made objects to actually cross the heliosphere's outer boundary. Measured drop in solar wind particle density and a corresponding rise in cosmic ray intensity from interstellar space. Around the same period, NASA's Interstellar Boundary Explorer, a mission designed specifically to image the heliosphere's edge from an Earth-orbiting vantage point using energetic neutral atoms, the picture that emerged did not match the smooth, comet-tailed bubble many earlier models predicted. IBEX data revealed an unexpected, bright band of energetic particle emission wrapping around a significant portion of the sky. Voyager's direct measurements, meanwhile, found a heliopause closer and more structurally complex than pre-launch predictions anticipated. An ongoing analysis of both spacecraft's data, compared against decades of solar wind pressure records, it responds to the sun's own long-term activity level, expanding and contracting somewhat as solar wind pressure rises and falls across cycles, meaning a quieter sun very plausibly produces a smaller shield. Here is what makes this genuinely unsettling. The heliosphere is not a decorative bubble. It is the primary shield confirmed. The boundary has now been physically crossed and measured by 2 independent spacecraft, and it is more complex and closer than older models assumed. Still not understood exactly how much that shield's size and effectiveness fluctuates with the same solar activity cycle we already cannot reliably forecast, and what that means for the radiation environment. Every mission beyond low Earth orbit, Voyager 1's crossing in 2012, was itself a small case study in how uncertain even a direct measurement can be at first. Instrument teams spent months arguing over exactly which combination of readings, dropping solar wind particle counts, rising galactic, cosmic ray levels, and a shift in the surrounding magnetic field direction actually constituted proof the probe had left the heliosphere, a debate only fully resolved after a chance plasma wave event let scientists directly measure the surrounding electron density and confirm it matched interstellar values. Even the single most concrete physical measurement of the heliosphere's edge that we possess required months of argument among the very scientists holding the data before they agreed on what it meant. The primary shield protecting the solar system from the deep radiation of the galaxy is a real, physical, measured structure, and it is still, in places, more of an ongoing argument. It gets stranger when you stop looking outward at the bubble and look back at the sun's own surface, because the sun does not rotate as a single solid body. It is a ball of plasma, and different latitudes spin at genuinely different speeds, a phenomenon called differential rotation. The equator completes a rotation in about 25 days. The polar regions take closer to 35 days to complete the same trip. A star spinning at two different speeds, depending on latitude, is already a strange enough fact that most people never learn it in school. The reason it matters goes deeper than the oddity itself. This differential rotation is believed to be one of the two central ingredients alongside convective plasma flow, driving the solar dynamo, the physical mechanism generating the sun's entire magnetic field, the leading theoretical framework developed and refined over decades and often called the Babcock-Layton model after the researchers. Turbulent transition layer deep inside the sun, called the tachocline, sitting between the churning outer convective zone and the more stable, uniformly rotating radiative zone beneath it. Here is the part that matters. The tachocline itself has never been directly observed. Its existence and properties are inferred entirely from helioseismic data, from listening to how sound waves bend and travel through the sun's interior. And while its general location and rough behavior are considered well established, the precise physical processes generating and sustaining the magnetic dynamo within it remain only partially modeled. Confirmed, the sun rotates differentially. The tachocline almost certainly exists in the location current models place it, and some version of the Babcock-Layton mechanism still not understood. The dynamo's behavior in enough quantitative detail to explain why cycle strength varies as much as it does. The engine generating our star's entire magnetic personality is running inside a layer we have never seen directly, reconstructed only through the physics equivalent of listening through a wall. Helioseismologists study the tachocline using two main observational programs, the ground-based Global Oscillation Network Group, from the way those waves bend and travel at different depths, the density temperature, and rotation rate of layers, far below anything a telescope could image directly. That work has mapped the tachocline's approximate depth and thickness with real precision. It has not yet produced a first principles model capable of predicting cycle strength. Every attempt to build a fully predictive dynamo model still requires tuning free parameters against a historical sunspot record. Technical way of saying that our best model of the engine driving the sun's magnetic behavior is still closer to an educated pattern match than a genuine first principles theory. Here is the part that widens the dread beyond our own solar system. Beginning in 2009, NASA's Kepler Space Telescope stared continuously at more than 150,000 stars for years at a stretch, originally hunting for the tiny brightness dips. In the course of that survey, Kepler's exquisitely sensitive photometer also caught something researchers had not specifically been hunting for: a population of sun-like stars similar in mass, age, and spectral type to our own, producing flares dramatically more powerful than anything ever recorded from the sun itself, so-called releasing energy in some documented cases thousands of times greater than the largest solar flares in our own historical record, including events comparable in scale to or exceeding the Carrington flare of 1859. Research teams analyzing the Kepler data, including work led by astronomer Yuta Natsu and collaborators, published across the 2010s, and age to raise an uncomfortable question directly in the peer-reviewed literature. Is the sun itself capable of producing an event on that scale? And if so, on what timescale might we expect one? The honest answer, stated carefully by the researchers themselves, is that this remains genuinely unresolved. Some analyses suggest slower rotating, more solitary stars like the sun may produce superflares less frequently than younger, faster rotating or binary companion stars in the Kepler sample, which would be reassuring if it held up. Other follow-up studies have raised methodological questions about how cleanly some of the observed superflare candidates can be distinguished from binary star systems. Here is what makes this genuinely unsettling, regardless of how that specific debate resolves. Nobody in the mainstream research community is predicting an imminent superflare from the sun, and the evidence leans toward our star's flaring behavior over the past several centuries. But the fact that stars sharing the sun's fundamental characteristics have been directly observed, producing flares in a different league, entirely means the upper bound of what a star like ours is physically capable of doing. Confirmed, Kepler directly observed superflares on stars closely resembling the sun. Still not understood precisely how rare an event of that magnitude would be for our own star across a time scale meaningful to a civilization. of what makes the Kepler superflare population so hard to dismiss is the underlying energy math. A typical large solar flare from our own sun releases somewhere on the order of 10 to the 32nd power ergs of energy. The superflares Kepler documented on sun-like stars routinely released 10 to 100 times that, with some extreme cases climbing thousands of times higher, potentially capable of stripping away significant fractions of a planet's atmosphere over repeated exposure if aimed at a world without a strong enough magnetic field. Researchers have proposed that some of the Sun's own past behavior, preserved indirectly in ancient tree ring carbon-14 spikes dated to specific years such as 774 and namely 993 of the Common Era, may represent solar particle events considerably larger than anything witnessed in the telescopic era, though still well short of true Kepler-style superflare energies. The Sun, in other words, may already have quietly exceeded our recorded history's worst storm. This is the one worst-case scenario worth sitting with honestly, and it deserves to be stated exactly the way the researchers who study it state it. We have two confirmed data points establishing that Carrington-class or larger coronal mass ejections are physically possible from our Sun. The first struck Earth directly in 1859, sparking telegraph lines on a planet with almost no electrical infrastructure. The second, in 2012, matched or exceeded that scale and missed Earth by roughly 9 days of solar rotation, striking empty space. Government risk assessments, including analyses conducted by agencies such as the United Kingdom's National Risk Register, and studies commissioned in the United States, have modeled what a direct hit from an event of that scale would do to today's infrastructure. Large numbers of high-voltage transformers, the components step power up and down across long-distance grid transmission, and that, in many regions, take from several months to over a year to manufacture. Satellite operators could lose spacecraft to radiation damage and atmospheric drag as the upper atmosphere heats and expands. GPS timing, used far beyond navigation in banking transaction synchronization, and cellular network timing could degrade for an extended recovery period. The honest, carefully hedged version of this risk, the version actual solar physicists and risk modelers put their names to, is this: magnetic energy building and releasing in an active sunspot region is a matter of ordinary solar physics that has demonstrably happened twice at this scale within 150 years of observation. Nobody serious is predicting a date. What they are predicting is that the event class itself is real, recurring, and that current infrastructure, resilience planning, transformer, we know the storm is possible because it has already happened twice. We do not know when the timing will run against us instead of in our favor. Grid operators in several countries have started installing devices designed to block the specific low-frequency induced currents, and international standards bodies have issued voluntary reliability guidelines asking utilities to plan for extreme space weather scenarios alongside more familiar threats like ice storms, but adoption remains uneven across regions and utilities constrained by cost, and no country has fully hardened its grid against a confirmed Carrington scale event, in large part because doing so competes for the same capital budgets as more immediately visible infrastructure needs. The risk is documented, modeled, and taken seriously inside the agencies that study it. Whether that seriousness has been matched by the pace of actual grid hardening is a separate, still open question, and it is the gap between the two that keeps this particular worst case. We began with a number too large to hold in the mind comfortably, a star so vast that 1 million Earths would vanish inside it, and we end somewhere quieter. Every question walked through here shares the same uncomfortable shape. The corona burns hotter than the surface beneath it for reasons still only partially modeled after 80 years of dedicated study. The 11-year cycle that governs space weather for the whole solar system keeps outrunning our best forecasts, as it did again with cycle 25. A multi-decade softening in that cycle's strength echoes faintly and without proof a quiet century that once coincided with a colder world. A 4-decade mismatch between predicted and detected neutrinos turned out to reveal something true and strange about the nature of matter itself. A flare in 1859 and a near miss in 2012 both confirm that our civilization's electrical infrastructure has already been within days, or would have been destroyed outright a century and a half earlier, of a direct hit from a storm we cannot yet reliably predict. A spacecraft built specifically to fly into the answer came back instead with new, unpredicted phenomena rippling through the data. The shield the sun blows around the entire solar system turns out to be closer, more complex, and more responsive to the sun's own moods. The engine generating the magnetic field driving all of this sits in a layer of the sun's interior we have never directly, and stars that share the sun's basic characteristics have been caught on camera doing something far more violent than anything our star has done in recorded history. None of this means the sun is broken or malevolent or hiding some singular terrible secret behind all of it. It means something quieter and, in its own way, more unsettling. The object we depend on more completely than any other single thing in the universe, 150 million kilometers away, hiding behind nothing but its own light. We are not looking for the sun's secrets in some remote unreachable corner of physics. We are looking directly at them every clear day, and we still do not have all the answers.